सब बदल दो.
You guys can hear me, right?
Yes, sir.
Okay. So let's begin now. Yeah. So for the first one, what kind of doubt? Anyone have any doubt or question? Which of the following statements is correct regarding the conjunctive normal form? So it's a CNF, right? So it is a conjunction of disjoint clauses, and empty clause indicates false. So these are the two correct options. And this is a very standard CNF kind of setting. So yeah, there is nothing much to discuss on this one. Okay, going to the second one. Which of the following statements are true according to the definition of satisfiability, validity, and entailment? Okay, so do you guys remember these definitions, or do you want me to pull them up for your reference?
Sir, I remember, sir.
Okay, anyways, I'll just quickly. So these are the definitions. A statement S is satisfiable if it is true in some world, it is unsatisfiable if it is false in all worlds, and it is valid if it is true in all worlds. And S1 entails S2. Whenever S1 is true, S2 is also true. Okay. So here it is asking S is valid if not S is unsatisfiable. Okay. So if not S is unsatisfiable, that means it is not true in all the worlds, right? If not S is unsatisfiable, it means it is false in all the worlds. So what can we say about S? That means S is true in all the worlds, and hence it is valid statement, right? So S S is valid if not S is unsatisfiable, and S is not valid if not S is satisfiable. These statements go hand in hand, right? And for the remaining two options, it is saying S is satisfiable if not S is unsatisfiable. That is also correct because it is a valid statement. And S if S is valid if not S is valid is clearly not correct, because if not S is not valid, that means if not S is not valid, what we can say that not S is not true in all worlds, right? And that means S is false in all worlds, which means that S is unsatisfiable. S is valid is not a true claim. Okay, is this clear?
No, no, sir. The third one is not clear.
Third
This
one is now clear.
that is S is satisfiable if not S is unsatisfiable.
Okay,
Yes,
let me
if
just.
not S is unsatisfiable means not S is false for all world. Does it mean that S is true for all world?
Yeah, if S is true, or if S is true for all worlds, it implies that S is
Definitely,
true for
yeah.
some
S is
world,
true for
right?
some world. Okay, that's the thing.
If S is true for some world,
Okay,
that means it is satisfiable, right?
okay.
So, like you can think of this is like satisfiable is the inner set and valid is the outer set. Like it like superimposes, or I can say it eats up the entire thing.
Sir,
Do we have?
sir, for last point, if
Mm-hmm.
it's written that not S is not valid, uh,
Mm-hmm.
so not S is not valid means not S is not true in all worlds. So it may be true in some worlds still. And when
That's
we
why it is not valid, because for a statement to be valid,
hmm.
it has to be true in all worlds.
So yes, sir. So when we put negation again, so still it will be that S is true in some world and false in some world. So it is not possible that it is not compulsory that S will be true in all worlds and hence it should be valid.
But
Yes.
for
Okay,
S
so
to be valid, it has to be true in all worlds.
hmm. But if not S is not valid, there are two conditions. It may be that S is false in all, not S is false in all the worlds, or it is false in some of the worlds.
So it does not matter if it is false in some or all. Even if it is false in some of the worlds, if it is false in some of the worlds, that means it is true in some of the worlds. If not S is true in some of the worlds, that means S is false in some of the worlds, right?
Hmm.
So
No,
we
no,
have to
sir, sir, actually, not S is not valid, means not S is,
okay.
I mean,
See,
false
we are
for all world. That does it mean that S
we
is
are
valid?
saying
No, no,
that
it
is
may
what.
be still true in some, false in, it may be true in some worlds,
See, what do
not
we
valid.
say when we say valid? We mean that it is true in all world. That is what you have to remember, right? If we are saying notice is not valid, okay, then what does it mean? It means that notice is not true. Notice is not true in
All world.
all worlds. Okay, notice is not true in all worlds if it is not valid, right? That means notice. So if we take the negation of this entire thing, what we will get? If it is not true in some worlds, that means
Sir, negation of this means S is true in
S is
true in any world.
S is false. See, it means S
Okay.
is false in some world.
No, no. So not true means false, na? So when we are taking negation of this, what does it mean?
Let me see. See, not true, it will become S, that not S is okay. Let me not write like this. That means if not S is not valid, that means not S is false in some world. Okay, let me write like this. If not S is not valid, that means not S is false in some world. Okay.
But it can be that it is false in all the worlds. Like,
In some, like, see, if we write all, it will be a much stronger statement.
hmm,
But for notice to be not valid, let us not say that not all, but it may be false in some world, right?
some world, yeah. Minimum some,
So
maximum all.
yeah. That's why I'm writing the lower one. All can be valid, like all is a necessary condition. But even if it is false in some world, it is a sufficient thing, right? You have
Hmm.
to understand this. It is what is sufficient. If you prove that it is false in some world, that means it is not valid. But for it to be like, if you are saying all, if it is false in all worlds, then it becomes like a necessary and sufficient kind of thing. So just put simply, if we are saying that not S is not valid, that means not S is false in some world. Do you agree with this statement or not?
Yes, sir.
Does anyone have any confusion in this part? If I write this, if I just write this, that notice is not valid, it means that notice is false in some world. What do you think of this statement? Is it correct or is it not correct?
Right, sir.
So that would mean that S is true in some world, right? If we take the negation of this, that means S is true in some world. In the worlds where where notice is false, this will become true, and wherever notice is true in those worlds, S will become false. So S is true only in some world. And since S is true in only some world, it is not valid. It is only satisfiable. Did you get this point or not?
Yes, sir.
Okay. Now moving to the third. So which of the following clauses can be entailed by the given set of clauses? So what does entailment means? So entailment means that whenever this is true, whenever this thing is true, this thing is also true. Okay. So this you can check simply by maybe a proof of reduction or something. Okay. So what we are asked this. Let me just copy this here. Get a new slide. Paste a text. So we are given these things: A not B C, B not C not B, B not C not B C, and B C. Okay. So from here, if we take these two, right? If we take these two, not B, B and not C, not B and C, we will get B, right? And if I make refutation with not B, it will give me a false set. That means the our assumption that B is false, that is not correct. Hence, B is true. So, a world in which this set of clauses is true, or this set of clauses is given, B will also be true. That we can show by refutation, right? Similarly, for if we have to show A, right, then can we by any clause show that A is also that a world in which this is true, A is also true? Can we show?
First and second.
So if we refute with A not B and C, we will get what first and no no. So you have to only pick only see you can only enumerate one variable at a time. Okay. So let's say if we do these two, then we will left with A C. Okay. Then if we take these two, then you will be left with A B. But there will be no resolution in which you can get A as a singleton thing and you can eliminate A. Can you think of any such place where if you take these two and you just do an and you will be left with just A? Will that ever happen?
No,
If we
sir.
resolve A
We
with
can
any
try
of these
C,
two?
sir.
Hmm?
Second and fourth one. We can try for C.
So if you do these two, you will be left with B, right?
Yes, sir.
Now you have used those clauses, right? Now you take these two, you will be left with AC, right? Now what will you use? If you use this, then you will get AB. Like if you use these two, okay. Let's say if you see you cannot use these two because there are two laterals that are going first at the same time, right? But we can use like these two. Let's say if we use A not B C, and if we use B not C or like B and C, then we'll be left with AC, right? And if we do AC with this, then we will be left with AB. And if we do this, then we will be left with AC. So that cycle is never just giving me a singleton A, which if you refute with not A, it will give me A. It will give me an empty set. That's why I think A cannot be proven.
So we can eliminate only one variable at a time.
Like if you cannot do A not B C, then you can take just like see what was the statement that was written here. They see the thing to do refutation. Let me just quickly go over that part. If you have to refute something, yeah, if you have to resolve something, then you have to show that P or A, comma not P or B or gamma, right? So if you are doing P or A, that means if you are doing B not C, right? B or not C. So this is what you are saying, that I have B or not C. Now if you take negation of B or not C, you will give negative B and negative C independently. What does the slide says? The slide says that it should be of the form P or alpha and followed by not P or beta or gamma. If you have a setting like this, only then you can refute P, and you can go on to say alpha or beta or gamma. And if you can refute S1 from S2, that means S1 entails S2. So that's why I'm saying that if you see B or not C, and if you are seeing here not B or C, that is not correct, because if you take negation of not B or C together, then it will give you what? If you see B, if you are seeing B and not C, right? So these are essentially B or not C, right? And if you take negation of this, then what? Then you will get negation B and C. So these are not two independent clauses. This is not same as not B comma C. Are you guys following this part?
Yes.
So that's why you cannot just refute these two together and give A. This will be incorrect. You have to consider them separately, and you can do as much as you want to, but you will never get A in a single clause, and that's why it is not like you cannot resolve away from this. That's why it does not entail. But I think you can surely do C. Can you do C? Yes, I think you can do C. Like if you take these clauses A comma not B or C, no, let's not do this first. If you do B comma not C and B or C, right? Let me just do
Sir,
that
if you
again.
do not BC and BC, then ultimately you'll get A and C. Will that be wrong, sir?
No, no, see, what I am saying is that if you do B comma not C, right, and you take B comma C, then you will get, then what will you get? Then you will get B, right? And from B and not B comma C, you will get C. And if you got C and you take it with negation C, you will get an empty set. So you can prove C from this set of clauses. Hence, C entails this thing. Now, what were you saying?
But how to, sir, what should be the approach to solve this kind of problem? Because if you
No.
start from the right, like BC and not BC, then ultimately you'll be getting A and C. Uh, I
If
mean,
you start with BC and
and not BC.
not BC, then you will just get C.
C, then again that you have to do with B, not C. That will give you B. And
Huh.
then again A, not B, C, and not
But
B,
why
sorry,
are you
B.
doing that?
No,
Why
no.
do you
So,
need to
so
do that?
that's what I'm asking. What should be the correct approach to do
No, no.
this?
See,
Solve this.
here you are given the options that you need to verify, right? Here you are given the options that you need to verify. So can you verify them? Or like can if you add a contradiction of this statement to the set of clauses, can you get an empty set? That is what is being asked essentially. If you can do that, that means it is entailed. What does refutation say? See,
No. Sir,
refutation says,
empty set. I'm not getting.
uh, what does refutation says that if from S1, if from given set of statements, you can resolve to S2, then S1 entails S2. Okay, that this is what refutation resolution is saying. See what I did here. If you just ignore this not C part, which I did for sake of explanation, if you just ignore this not C part here, we were able to prove see we were able to show that doing some sort of by doing some sort of refutation steps, that yes, we can get C and we can get B. And I think we can also directly get C by doing not B or C, and if we do just this, then we will get C, right? If we just resolve these two, we will get C. But by taking any two clauses, okay, let's do it like this. Just take any two clauses from these four sets from this set of four clauses, and just take any two clauses, right, from this set of four clauses. Now, can you show that you can derive A, B, C, or empty set, right? If you can show that, that means you can show that they are entailed. Now, were we able to do it for all? No. We were only able to show for B and for C that if you take any two clauses of this set, you will be surely able to get B or C. And since these clauses are given as true, and we are able to show B or C can be derived from the set of these clauses, that means B or C is entailed by these set of clauses. Is it clear now? Or do you want me to go over this once more?
Sir, for that first one, B1, can you like tell that what and all clauses do you take?
Just give me. Okay. See, so what we have this thing. Okay, we have this thing. Okay, let me just put it here. Now you pick any two clauses. See, what does this says? If you are given P or alpha and not P or beta or gamma, and if you resolve this, you will get alpha or beta or gamma. Okay, this is what it is given in the slide. Let's just
Hmm.
follow what the slide says. Okay, now you are given that these things are known, these things are true, right? That is what the question says. So if it is asking that is entailed by, then you have to assume that these clauses are true or these clauses are known to you. Okay. Now since these clauses are known to me, what I can do is, see, I can use these two. I can use these two to resolve it to C. Right? So using these two, I have essentially shown that I can obtain C by resolving these two clauses, and I can entail, or I can resolve B from these two clauses. Okay.
Yes, sir.
Now it is known that these are true, and it is known and these are true. So you can entail B, you can entail B and C. But can you show by resolving these clauses, by taking any two clauses from these sets, can you show by resolution that you can obtain A? If you can, that means A entails. Otherwise, you cannot show.
Okay, okay. Yes, sir. We cannot because there is no clause with
Exactly.
negative A or something.
Exactly. Because see, what does the slide says? The slide says that if you can resolve S2 from S1, then S2 entails S1. That is what the slide is saying. And we have just shown that we can resolve C and B from these things. So it entails.
So,
Okay.
sir, we don't need to take all the clauses and solve them. Like any
No,
two
no.
clauses should be
That see
sufficient.
that I was doing earlier, but then I realized that we have to show it entails. And
Okay.
while checking here, see, entails only holds when you can resolve S2 from S1. When you resolve S2 from S1, and this is your S1 and this is your S2.
Okay. Yes, sir. For this resolution, only two clauses we need.
Only two clauses. However, if you were to show like these kind of things, that you are given many clauses and then you apply resolution, then it is fine. See, you can argue that I can use one or more, but I don't think if you use even more clauses than two, or if you do resolution twice, you will get A from any of these things. Have you checked? Like, have
So
you
if you
checked
take,
with these things that
sir, if you take first two, then what it will resolve to?
first two will not be true, because see what I said, that for resolution you need to have a condition like this, that it is P or alpha, okay, and there is not P or beta or gamma. Okay, this is what you have to have. Now negation of B or not C is not B or C.
Okay.
Negation of B or not C, you have to see that this is your P and this is your not P. Okay, if only this is there, from here you can resolve alpha or beta or gamma. Otherwise, you cannot resolve alpha, beta, gamma out from the condition. Now, is not B or is not B, comma C negation of B, comma not C? Do you think that is correct?
No.
What is b comma not c? B comma not c essentially means b or not c. Now if I take negation of this, what will I get? I will get not b and c. So
Yes.
these becomes two independent clauses.
Hmm.
Not b or c is not negation of b or not c. That is what I am trying to explain. Hence you cannot resolve these two simultaneously. Okay. So now moving on to the next one. So assume you are using DPLL algorithm with mom's heuristic on the following CNF formula, and what is the next variable that you will be branched on? A comma not B C, not B comma C, not C comma D comma E. Okay. So for mom's heuristic, okay, for mom's heuristic, most occurrences in the clauses of minimum length. Okay. So which of the following? Let me just do this. So of these clauses, A comma not B comma C, not B comma C, C comma this, which clause do you think? Like which first of all, what is the minimum length clause? Let's fix that. So what is the minimum length clause here?
DB.
Okay, so no,
Not B and
what
C
is the
also.
minimum?
B,
What is the length of the minimum length clause?
2.
Two.
Two, two.
Yes. So what are the clauses of length 2? It is not BC, okay, DB and EA. These are the two minimum length. These are the three minimum length clauses. Now, which variable occurs the most? So B is occurring twice, one in negative form and one in its true form. Then there is C once, D once, E once, and A once. So since B is occurring twice, we will pick that one. Okay.
Yes, sir.
Is it clear now? So we will pick B, right? Now it is saying that if you set your selected variable to true, what is the formula you will obtain followed by
Sir,
repetitive
I have
elimination?
a doubt in first and second question, sir.
First and second question. Okay. Yes. Can we just do that after this question, if you don't mind?
Okay, sir.
Yeah. Okay. So we picked after applying Mom's heuristic. It is said that we pick B and we set B to true. Okay. So what will the new state look like? So it will look like A false or C. So essentially A or C. This will become false or C. So it will just become C. This will become not C or D, naughty. This will become not a comma e. This will become a comma not c. This will become true, like since b is true and d or b will be become true, and then we have e or a. Okay. So do we have any unit literals? Yes, we have a unit literal which is c here, right? So we will set c to true. Okay, we will set C to true. So that will give us, this will be resolved to true. This is already true. This will become D comma naughty. This will become just E. This will become true, and this will also become true. Okay. Is it clear how this is happening, or should I go? Should I explain?
No,
No,
sir.
Okay,
No,
sorry.
sir.
it
Got
is
it.
clear.
I think I did a mistake. Sorry. It is not C that is being. It is C that is
You
being set.
skip one step, but it is correct.
No. I actually set A to true instead of setting C to true. Sorry, my bad. That will be the next step. Yeah. Sorry. Okay. Apologize for this. Yeah, so we are setting C to true in this step because C is the only unit literal here. And here we have, uh, what was the clause here? Not A, E, and we set B to true. So we will get A comma not C. Okay. Since C is the unit literal here, we will set C to true. So this clause will resolve to true. This will become true. This will resolve to D comma not E. Okay. This will be not A comma E. This will become this will become A, and this will become E comma A. Okay. So now we have A as the unit literal, so we will set A to true, right? If we set A to true, we will get D comma not E. We will get E. This will become true, and this will become true, right? And now we have E as unit literal, so we will set E to true, right? And if we set E to true, we will just be left with D. Is this correct? Does anyone have
No,
any
sir.
question here?
Sir, we won't be left with anything if we set E2 true.
What did I miss? Did I do something wrong?
Sir, the D comma E you made mistake, sir.
Now we have to do
Uh,
uh, assign D to true.
No, no. Correct, correct, correct,
no, no,
correct, sir. Correct, sir. I made mistake.
no, no, no. This is the only unit literal. So, yeah. This is the only unit
Yeah,
literal
I
job.
think
So
the
we'll
answer
assign
is
it.
D, sir. Option D, sir.
Yeah, option D. Yeah. We will be essentially left with nothing. All clauses are resolved, and yeah, this is the final assignment that we get. So we get B true, C true, A true, E true, and D true. Yeah. If we do this, then it is solved. Yeah. So question number 1 and 2. What are the doubts? So someone had doubts in question 1 and 2.
Yes,
Can
sir.
you?
I have no doubt, sir.
Mm-hmm. Yes,
Sir,
please
I
go ahead
can't
now.
able to get the question, sir. What was the question asking? I can't able to understand, sir.
Okay. So the first question is, which of the following statement is correct regarding conjunctive normal form? Okay. So do you understand what? Say you do understand what is conjunctive normal form, right? Conjunction normal form.
Sir, conjunction
It
of
is a
form means it is a combination of both the forms, sir.
no. It is like a product of sum.
Okay, okay, sir.
So if it is a product of sum, that means it is like this. So you understand what this notation means, right?
Yes, sir.
So it is what it is. Can you tell me what it is? So this will become A or not B or C and not B or C. So this is a conjunction of disjunctions. That's why it is written like that. It is a conjunction of disjunction clause. And we have seen already that an empty clause indicates false. So these are the only two correct options here. Is it clear now? The first one?
Yes, sir. It's clear, sir.
And second one, what was your question?
No, sir. Second one is okay, sir. I clear, sir.
Okay. No, if you have any question, you can ask. Like we did a discussion some time back, so I can repeat if you want to.
No, sir. I have doubt only week 8 assignments, sir. First question only in week 7 I have doubt, sir. So I clear the doubt. In week 8 assignment I have doubt, sir.
But week 8 is the are the solutions out yet?
No, sir. No, sir. We have to give it by 22nd.
And I cannot discuss, right? Ethically, I cannot. That we will discuss in this week, in this week's doubt class.
Yes, sir. Minimum values means does it mean minimum parameters?
Yeah. You can
Yeah.
think it
Okay.
like that.
Okay.
Sir, when we will discuss week 8 assignment, sir?
We will discuss week 8 assignment this Friday.
Sir, I have a doubt, sir. Tomorrow is the last date for submission of assignment, sir. So today we
Yeah,
can start, sir.
no, no, no. See, the point is we are doing it in a latter way. Like it is not a former way. I always do the assignments of the previous iteration to give you the idea that what is coming this week. But for week 7, I was not able to conduct a session on Friday, so that's why I'm doing it on Tuesday. But we will still discuss it like it was a Friday session.
So only three questions I have a doubt, sir. Only
No, but
algorithm sums, sir.
the solutions are not out yet, so I cannot discuss the solutions. Or like I can just clarify your doubts, but I cannot tell you how to solve it or what could be the solution. That would be unethical, I assume. I
Okay,
can
sir.
I can clear the doubts that you have that we will come to out just after we finish this, but I will not solve the questions. I will not solve the exact question.
No, no, okay, sir, that's fine. That's fine. We can discuss, sir, about if you have any, I mean, if we have any problems
Uh-huh,
in
yeah.
understanding the
That we
concepts, then that you can do.
definitely
Okay, sir, right.
that we will do. So I think the remaining questions are purely theoretical. So okay, except for question number 10, which I will solve.
Sir, question number
7, 8.
8, please, sir. Could you please discuss question number 8? 8 and 9 also.
Okay. There was also this question last time, right? That whether Voxat is complete or Voxat is sound or something like that, right?
Yes, sir. That we could find only on Google, sir.
So if we just if we just Google, you'll find that it is there. However, this asymptotically complete thing I did not find, but yeah, I found that it is sound.
Sir, some infinite time, like it, it will be complete, sir. Like I think they're assuming like that.
See, I mean, yeah, you can always say that, but the underlying assumption would be that if the clause is satisfiable, only then it is asymptotically complete. I think that is what we were discussing last time. If you remember that in the book it states that, so how does this box set or random walk algorithm or random restart algorithm works, right? The idea is that you keep on you randomize from a new state, right? Now if it would be asymptotically complete if let's say you are restarting randomly and you hit the goal set as a start state in one of your restarts. If you hit the if after restarting your goal state becomes a start state, then you found a solution, right? But if the statement itself is not satisfiable, you will never find a solution. So it is not guaranteed to be complete. But I think the underlying assumption here is that yes, the statement is satisfiable and then it is asymptotically complete. Then I will not argue that it is not incomplete. Okay. So yeah, that was one point of discussion that we did need to do, but I think it is covered here only. Okay. In question number 8, it is saying which of the following are correct about soundness and completeness of RE and forward chaining. Resolution and forward chaining as proof of systems for as a proof of systems for inference in logic. Okay. So see, we just now showed that for like we saw this case, right? A comma not B comma C, that clause. There we could not prove whether A is valid or not. Whether we can show A, whether we can derive A or not. And forward chaining, resolution and forward chaining, these kind of algorithms can only tell you a thing is complete by some. So it can tell you whether a given statement is true or not, but it cannot always tell you that a given statement is not true. So that's why they are sound algorithms, but they are not complete. Are you clear about the distinction of sound and complete? Are you guys clear about this distinction?
Yes, sir. Sir, you said some line just few seconds back. Like they don't. Can you repeat that again, sir?
Yeah. So what I was saying that in this resolution and forward chaining kind of systems, you cannot tell for sure that a clause is satisfiable, or or a solution exists there. But if a solution exists, it will be definitely able to find it. So the concept of soundness is that if like it should tell you the truth whenever asked for. So if you give it a question, and if indeed it can, if it is true, then it will tell you it is true. Then it is sound. But if it cannot tell you that this is not true, then it is not complete. Because for complete, it should be able to tell you that this is not true.
Okay, sir.
So see, that is what I was trying to clarify last time also. I think I have written that statement somewhere. Where did I write? Yeah. So sound is if the result it produces is always correct, and completeness is if the result is produces. So whenever we ask for a result, it tells you that the result is correct. Then you can say that the algorithm is complete. It is a message. Okay. Yeah. Now coming to the last one, CNF formula, which is the equivalent. Okay. Equivalent CNF
Sir,
formula.
ninth also. Ninth you left.
But this is discussed in the slides, I think. I don't have the screenshot of that particular slide, but it was discussed in the lecture. When professor was talking about, I think, this graph, he clearly told that which part is which part. You can refer to the lecture for this one. Unfortunately, I don't have that particular discussion
Okay,
here
okay,
right
sir.
now.
Okay, sir.
But I think in the first 5-10 minutes of the first lecture itself, you'll get the answers to this question.
So that they're discussed about knowledge representations. That.
Yeah, yeah. So when you come to this slide, I think this is in the
Hmm.
first 5 minutes of the
Sir,
lecture.
in that itself, you can see in that graph. That graph.
So FOFC, and so what is the question asking? So the question is asking FOL and BN have similar. Okay, FOL is first order logic and probabilistic propositional logic. So probabilistic propositional logic and first order logic. And these are in different ontological, have similar ontology and different epistemology. Okay. Yeah, I think from this figure also you can understand this part. Is the figure visible or should I? First order predicate logic and probabilistic, these are these are in the same ontological commitment, but these are in the different epidemiology. Yeah, because from the figure here you can see that first order predicate logic and probabilistic. Anyways, if you watch the video, there you will find more clarification. Is it fine? Like if I'm just saying, if you refer to the first 5 minutes of the first lecture or something, then you will get the idea. Or if you just refer to this slide. So these slides are also available in the folder. I hope you have access to these, right?
No, sir.
You don't have access?
Sir, BN is not there. Bayesian networks is not there. First order propositional logic
So,
is
so Bayesian network
Bayesian's.
means probabilistic propositional logic.
Yes, sir.
okay.
Probabilistic propositional logic. So
That is there.
that would mean probabilistic propositional logic would mean this here,
Okay. Mm-hmm.
and first order propositional logic would be this propositional logic.
Yes, sir. They have same
So these are
ontological
in the
but
same
different.
ontology but different epistemological commitment.
Yes, sir. So then, what is this one predicate? First order predicate. Okay, there are direct relations like which you used to
So
study
the
in maths.
first order logic just have these statements that there is a statement P, there is a statement Q. Now, when it comes to predicate logic, there are also relations between the there is also a relation there comes relations between the statements. So if you say like John is a person, and Mary is a person. So in first order logic, you can uh, simply write these as two independent statements. So for example, you are saying J as the person is John. Okay, so that the person is John. Okay, then P is a statement that person is, let's not say P. M is a statement that person is Mary. Okay. Now, if you want to say that John is John is married to Mary, so then you need to show some kind of relation, right? And this relation is married, which is a function of two such statements. So married J comma, sorry, married J comma M. So whenever you define such predicates, so these are called, this will become predicates, and there is a relation between predicates J and M, married J comma M. So then this becomes predicate logic, and you can, there is a separate class of refutation resolution for resolving these kind of predicate logics also. So in first order logic, you have these statements, and these are just independent statements J and M. But if you want to show relations or something between these two statements, you need a function which takes these objects as input and tell you whether this is true or false. So it will have two values, either true or false. Like if they are married, this will be true. If not, then it will be false. So then it becomes predicate logic, which is different from a simple standard first order logic. However, this distinction was not covered in the lecture, so I did not find it necessary to cover in tutorial or something like that. Yeah. So finally, coming to the last question, CNF equivalent formula of this statement. Okay. So that would be here. Someone was saying in the chat that the recordings are not accessible. Is that the case?
Sir, not recording, sir. Those slides.
Slides?
Like
But if you check so you have the access to this sheet, right? Let me see. You have
which
access to, where did it go? PMRF. Yeah, you have
yes, sir.
access to
Those
this sheet, right?
yes, sir. Those Excel sheet is there.
So here, if you go to the presentation folder, so under my row, you will always find this. If you go to this folder, there you will find section for slides. If you open the slides, you will find the slides for all the weeks.
No, sir, this was not available.
No, but if the sheet is
No, we yes, yes, but this is not available. Only in slides are not available. Your presentation was available.
haha. So this slide that I am showing you right now here,
Hmm.
these slides are
No, no,
available,
this
right?
was not available.
No, but that's what I was saying. That if you go to Google Sheets, there you have the access to these slides.
In Google Drive, sir, my drive, if we access this, when a problem solving session, if you click that, then
And I'm not sure why you don't have access, but like I have given it view access to everyone who has the link. You cannot access that link, or like when you open it says that request access. What is the issue?
Sir, no, sir. It's I got it, sir. It is available, sir.
Yes.
I was not knowing the link.
Yeah, I see that someone is there. Like I can see this anonymous camel
Sir,
icon.
this I think me, sir.
Yeah. Okay. The last question, which of the following is the formula? I think I already copied it there. Okay. Yeah. So this you can resolve to. So P implies not Q will become not P or Q. This implies not Q or R, right? So this is the first step. Now from here, you can go to not of not P or Q, or not Q or R, right? So this will become P or not Q, sorry, P and
And
not Q, or not Q or R. Okay. So now we will distribute this and over this or. So it will become P or not Q or R, and not Q or not Q or R. So this will simply be resolved to P or not Q or R, and not Q or R. Is this the correct answer? Oh no. What did I do wrong? Is P implies Q and P? Oh, it is P implies P implies R. Uh, not not Q implies R. Yeah, that's my bad. So this will be not P or R. So this will become, okay. Let me just take it to the next slide. What am I doing today? Sorry, this is not the right thing. This is the right one. Uh, Yeah. So from here we will get not P or Q implies not Q, not P or R. Okay. Then we will get not of not P or Q, or not P or R. Then we will get P and not Q, or not P or R. Now we will take this and distribute this over this or. So we will get P or not P or R, and not P or not Q or R. So this will resolve to true, or R. This will resolve to true, and true and not P or not Q or R will result simply to not P or not Q or R. So now do we have this correct? Not
yes,
P
sir.
or
Right.
R. Okay. Nice. Okay. Admit. And yeah, so now we can discuss the problems that you have in week 8 assignment. Let me just open it. Is it week 8? I think it was this one. So yeah, what are the questions or problems that you have in the week 8 assignment? Am I audible?
Yes, sir.
Yeah, so you guys were saying that you have problems in this week's assignment for Bayesian network.
Yes,
So
sir.
what?
First is complexity of Bayesian network, time complexity.
Where is it asked anywhere?
Not directly.
I don't remember professor discussing any such concept about time complexity. But here it says, you see, here it is saying that if you have, so yeah, if you have D as the maxarity, which means that number of values that it can have, and n as the number of random variables, then complexity would be d to the power n. This is the worst case time complexity of enumeration.
So
Now similarly,
basically, it is
if
2 to the power n. I mean, if it is binary kind of thing.
if it is binary, yes, exactly, it is
Yeah,
2 to
so
the
it
power
is
n.
always
But this is
exponential.
the complexity of enumeration. This is the complexity of enumeration. It is not the complexity of Bayesian nets. So in Bayesian nets, you essentially bring down n. Essentially bring down these stable entries, right? So here it is saying that if you apply the notion of conditional independence, the third entry is reduced to 12. So for n independent bias coins, 2 to the power n will just be n. So that will all boil down to how you are basically arranging your zone distribution. So that's why I think there is no comment on the time complexity in general, because I don't remember seeing any example of time complexity being like. Mhm. Any other question?
So for a particular joint distribution, is it going to be a unique base net? Or we can have multiple base net for the same joint distribution?
See, there exists a unique. See, this is a
This is
okay
to be
question.
answered because
Uh, so I think this was discussed in the class
no,
that
sir,
for
it was
a
not
given
discussed.
staging. No, no, no. I think professor did made a comment on this. Like I can draw a Bayesian network in one way. You can draw a Bayesian network in another way.
That's
Like
possible.
here in this
Yes.
John and Mary example, he said that
Hmm.
I can draw it in any way I want, but the optimal order would be like that is something that you need to think. And what was the other question? Are there any further questions regarding the clarification on this week's assignment?
No, sir.
Okay, and let me see, uh, because I think there was no assignment. Was there any assignment this week? My courses. Oh, there is no. Uh, okay, let me see. In week 9, are there any Bayesian network-based questions we can solve? Assume likelihood, unspoon. Yeah, I think there is no sheet for this week's question. Let me see if I have something offline. Okay.
Sir, shall we leave the class, sir?
No, no, just wait. I will see if I have some practice problems. Otherwise, yeah, we can leave this class. Can you look at there is alarm as well? Because it's more likely to fail when the core temperature gets too high. Okay. Okay. So yeah, we can quickly solve some questions that will give you idea. Entire screen. Let me share.
Sir, can you explain the different way of writing conditional independency?
Conditional
Like
independence. Okay.
with different nodes, like 3 or 4 parent is there, or 2 or 3 child is there, likewise.
Like this. So what, like in this question, or what? What is your specific question like?
In general, any questions?
So check it.
Here there are only
Yeah, yeah.
2 parent. Can it, if there is more than 2 parent, how to write it?
So here are only two parents, right? So alarm is dependent only on burglary and earthquake. Yeah. So what is your question?
Sir, if there are 3 parents and 2 or more child, how to write the independency?
Independence. Okay. Let me understand. So you are saying that, okay, if I have this node A and it has three parents, let's say P1, P2, and P3, and this parent has three childs, C1, C2, and C3. So what is your question now?
So how can we write independence between P3 and C1?
So they are conditionally independent given A. So if you know the value of A, C and P3 are deseparated, right? See, this comes from this variant. So this is the first case of desseparation, that information can flow between A and C if and only if we do not have evidence at B. But if we know B, that means A is deseparated, and A is deseparated with C given B. So given B, A and C are conditionally independent. So if it were if you have something like P of C1 conditioned on A comma P3, and if you know A, you can just remove P3. You can just say that this is equal to saying P of C1 conditioned on A. It is conditional. C1 is conditionally independent of P3. I think that is what was discussed here, right? Because if you see in this John Mary case, that's what Sir kept doing. Like if you have to show that burglary happened, given John called is true and Mary called is true. So we wrote it like this: P of B given J comma M. So P B J M comma P J comma M, and then we add this P B J M and summation E comma A P B A J M. So the smaller indices are for which we know the value, and bigger indices are for which we don't know the value. Now, since here we know only the value of the child, there will not be any case of conditional independence. So we need to segregate the network entirely, and we know that alarm is C. This J is conditionally dependent only. So J is dependent only on alarm, but not on earthquake. So we just write it like J given A, and M is dependent only on alarm. So we write it as M given A, and then A given E comma B, and then P of E and P of B. That is how this entire thing is segregated.
Okay, sir. Thank you.
Yeah. So here is a question for you guys. So assume the base net from class is a okay. There is someone waiting in the queue. Assume that the base net from the class is a perfect representation of world. Okay. Now let me just fit it to it. Huh. Now you know that you do not have a stomach bug. Now, if you were to vomit, would it change the probability that you had a fever? What would you comment on this? Is this statement true or false?
Sir, can you repeat
So,
the statement?
yeah. The statement is written in the end. So, you,
Okay,
kn-
okay.
It's a false, sir.
ah, why?
So because the independent of the two variables depending on the stomach bug, sir. So it is false, sir.
If you were to vomit, would that information change that you had a fever? When you are saying it is false. Okay. But why false? You are saying why is that false?
So because the two independent variables belong to the same stomach bug, sir. So I say the answer is false, sir.
But fever is also dependent on flu, right? So fever is dependent on stomach ache and fever is dependent on flu. Okay, so let us look at this condition of Bayesian net. So what do we know? So we know that information can flow between A and C if and only if we do not have any evidence at B, right? Yeah. So do we have evidence at B? Like in this situation, what is B? In this situation, B is stomach bug, right? So if we know stomach bug, do we know that it will lead to like what do we know? If we know stomach bug is if we do not have stomach bug, and if you were to vomit, would that information change the probability? And the answer is false. And simply because two variables are conditionally independent given stomach bug, which is because of the second variant of deseparation. Right? What are the second variant says? Two, yeah, this one. It is a diverging connection. Information can flow between A and C if and only if we do not have any evidence at B. So if you clearly understand the criteria of separation, then you will have no problem identifying which variables are conditionally independent.
Sir, for fever, like we can also use the second rule, that Markovnikov rule, that it is dependent only on the parent and child. Fever doesn't have any child and other parents of my child. So there are
So
nothing. So
see,
it is independent.
given stomach bug, you can only say that fever is conditionally independent of vomit. However, you cannot say that fever is conditionally independent of cough. given stomach bug,
Hmm.
right? You can only say that fever is conditionally independent on vomit.
Yes, sir. Only
And
fever and vomit we have to prove, no, sir. Cough
uh,
we don't have to
for
prove, sir.
cough, you need to know what is the status of flu.
Hmm. Yes, sir.
If you don't know flu, then you cannot say about what is the situation of cough.
No, sir. I was saying that we can use desuppression also, and also that second rule, sir, which I discussed, Markovnikov, that it is dependent only on the blanket around the parent, child, and other
I said the
parents or.
Markovian blanket concept. Yeah.
Uh,
This one, yeah.
and
Given
if we
Markov
take
blanket access,
if we
not
take
even this
fever,
one. The first one itself is fine.
it is dependent only on the parents and the other descendants. Yes.
Yeah, in not second here explicitly first rule applies. See, given parents, X is independent of its non-descendants, right? So for X, if you know U1 and UM, so Zij and Znj it is conditionally independent of all these things. Zij to Znj.
Yes, sir. This also we can use. So,
This one, yes. And it is shown here also that given alarm, yeah, given burglary and earthquake and alarm, John calls, Mary calls, and radio. So yeah. Okay, so this statement is false. Now there are some other questions. This is not Bayesian, this is not Bayesian, this is not Bayesian. Yeah, this is a Bayesian question. Now in your local power station, there is an alarm that senses when a temperature gauge exceeds a given threshold. The gauge measures the temperature of the core. Consider the Boolean variable A alarm sounds. If A alarm is guilty, FG alarm is gauge is faulty, and the multi-value discrete nodes G gauge reading and T the actual core temperature. Okay, so draw a Bayesian network for this domain given that gauge is more likely to fail when the core temperature gets too high. Okay, so can you design a Bayes net for these for this setting? So first of all, let me ask you this: what do you know in the current setting? That which variable you say is dependent on what variable? Can you make a guess? So read the question, take some time, and then tell me. Then can you tell me and which variable is dependent on what variable?
so should we use all the like variables?
You can just tell me a relation, right? So can you tell me that whether who will be the immediate parent of what? Can you just give me an idea of that?
So T will be immediate parent of
Yeah, so
alarm.
T will be the root essentially. It will not be the, so T will be the root because everything is dependent on a temperature, right? So T will be the parent. Let's say I give you that information, and I'm telling you that G is the gauge reading, FG is when gauge is faulty, right? And then you have FA, when the alarm is faulty, and Boolean variable A is when the alarm sounds. So I think A will be the ultimate child, or it will be the last child, right?
So
Because you
no,
have to show
I
that whether
think node G
alarm,
is the variable belong to the FS and FG, sir.
the node G belongs to me. So G depends on FG or or FA depends on G. What can you say?
FG, sir.
A
So you have
alarm depends on G.
yeah. So see what essentially what I'm asking is, let's say you have these variables. You are given these variables, right? You are given. So we have figured out two things, that there is a temperature variable T and there is an alarm variable A, and in somewhere in the middle there is a gauge variable G, right? And we know it says in the question that
Temperature influences gauge. Yes, sir.
given that the gauge is more likely to fail when the core temperature gets too high. Okay, so this is a statement that you know, and Fg is gauge is faulty. Okay, so gauge reading will depend on both these inputs, right? Okay, now let us see the final thing. So let us, so this part is clear, right? Why this is happening? It is saying that gauge is more likely to fail when the core temperature is high. So Fg will influence G, right? Because whether gauge is faulty or not, that will tell you whether the reading of the gauge is correct or not. And it is more likely to fail when temperature is high will give you this link, this dependence link, that T goes to Fg. Because if temperature gets too high, gauge will fail, and when gauge will fail, it will temper with the readings of the gauge. So there is this directly one path and indirectly one path in case the temperature is not too high. This path is this will not fail, and we can rely on the gauge reading, right?
Sir, how does faulty guards influence the gods, sir? That I'm not getting.
So
Temperature, if
faulty
it is
gauge will tell you whether the gauge is faulty or not, right?
yes, sir.
So if the gauge is faulty, you might not you will not rely on the gauge readings. But if the gauge is okay, so it in that sense it influences the gauge reading, and gauge reading and alarm is faulty or not, that together will influence alarm. So is this Bayesian network structure clear?
Okay, sir. And so similarly, faulty alarm will influence the alarm also.
Because if alarm is faulty, then if like that depends whether alarm is faulty or not. And if it is faulty, it will influence. If it is not, then it's fine. Is everyone fine with this?
Yes, sir.
Okay. So the next question, that suppose that there are just two possible actual and measured temperatures, normal and high. The probability that the gauge gives correct temperature is X when it is working, but Y when it is faulty, right? So give the conditional probability table associated with G. So see, we know that G is dependent on Fg and T, right? We know these two things, that G, it is dependent on Fg and T. Now it is saying that there are just two possible actual and measured temperatures, normal and high. So T has two values, normal and high. And the probability that the gauge gives the correct temperature is X when it is working, but Y when it is not working. So Fg essentially takes two values, faulty and not faulty, and X when it is working and Y when it is not working. Okay. So there will be two scenarios: Fg when G is true, Fg is true, that is gauge is working correctly, and Fg is false when the gauge is not working correctly. And for T similarly, we have two values, high and normal, and for G, that whether the gauge is working correctly or not, that is high or normal, right? So when temperature is high, it is more likely to fail, right? So we have Y here. And similarly, when temperature is normal, it is 1 minus Y. And oh, sorry, Fg is okay. Sorry, I just, yeah. So Fg is the Boolean variable which tells you that gauge is faulty, right? When that variable is true, when Fg is true, that means gauge is faulty. And when gauge is faulty, it gives you the reading with the probability Y, right? When temperature is high, it is more likely that gauge is faulty. That's why temperature given high has value Y when gauge is faulty. And when temperature is normal, it is 1 minus Y.
Sir, the X is wrong, sir. The
No, no.
gauge gives the correct temperature is X. So
Fg
F
is true means, see, what was Fg? You have to understand what was Fg. Fg
faulty
means gauge
gauge.
is faulty.
Yes, sir.
That's why it is the negated way.
Sir,
Y is
Y1
here.
is Y is correct, sir. But for X, sir, it gives the correct temperature when X is working. So the temperature will be normal, no, sir. So that 1 minus X will be X here, I think. Gives the correct
Probably
temperature.
the gauze gives the correct temperature is X when it is working, but Y when it is faulty. So X when temperature is high.
So when temperature is normal, shouldn't it be X?
In the question it says gauze is more likely to fail when the core temperature gets too high, and G is the gauze reading.
Yes, sir.
G is
For I
false.
think for normal, when G gauge is normal and temperature is normal, then it is X.
See, when the gauge is normal and temperature is normal, it is X. That is there, right?
Yes.
And we know that it is not faulty. And when temperature is high, gauge is also high. That means the reading is correct. We
Temperature
know
is
that the gauge
okay.
is not faulty. When temperature is high, gauge reading is also high. That means it is working correctly.
Okay. I mean, this means that it is sustaining that high temperature also, and it is
That
again.
that means it is reporting the high temperature correctly.
Okay.
See, the 1 minus x will occur only when the reported value is different from the actual value.
Okay, sir.
Did everyone understand this point or not? You can raise your hand or you can just speak. Because I don't see a lot of people, so it's fine. Yeah. See, what does this category implies? Let us first go over that. Okay. So FG is true means that the gauge is faulty, right? And FG is false. That means that the gauge is not faulty. Okay. Now, if the gauge is faulty and for higher temperature, the gauge's reading is also high, it means that the reading is not correct. And when it is not correct, it is with probability y. So that's why even when temperature is high, if gauge is reporting it high and it is a case when it is actually faulty. So this will become this will be y. But when temperature is normal and it is reporting it as high, that means it is broken. So that will be with 1 minus y. Because that is actually the correct reading it is giving. Similarly, in the row below this, when temperature is high, the gauge is giving normal. That means it is giving incorrect reading because it is faulty. That happens again with the probability y, and here it is giving high as normal. That means it is doing it is doing the opposite. So it is 1 minus y. And similarly, whenever it is reporting normal as normal, that means it is giving the wrong value, and that happens with the probability y. So whenever it is reporting the same value, that when temperature is high, gauge is also high, given that the given that the gauge is faulty, the reading is incorrect, and that is happening with probability y. So that's why the these two values t high g high and t normal g normal are y, and t normal g high and t high g normal are 1 minus y. Similarly, when fg is false, given that fg is false, that means the gauge is working correctly. Whenever it is reporting same temperature and gauge level, it is working correctly. Then it is probability x. So t equals to high is x, g equals to high, that is x. When t is normal, g is high, that means there is a discrepancy in the reading. That is happening even when the gauge is not faulty. So that will be 1 minus x. and vice versa. If G is normal, T is normal, it will be X, and if G is normal, T is high, it will be 1 minus X. Is this clear now? Okay. In which case, it never sounds. So give the conditional probability table associated with A. Okay. So alarm works correctly unless it is faulty. So if alarm is not faulty, then the alarm works correctly, meaning that it sounds only if gauge reading is high. Okay. So when will the when see when will the alarm go high? The alarm will go high, assuming it is working correctly, only when the gauge reading is high. Okay. Only in that case it will go up. Otherwise, it will not go up. Okay. So when the gauge is normal, but the alarm is faulty, what will the alarm go up?
Sir, what about the
Can,
temperature, sir? It is not given anything about temperature.
so temperature is readed by gauge. See, the temperature is readed into gauge, and gauge detects whether the detecting by reading gauge you can say whether the alarm will go whether the alarm will ring or it will not ring.
Okay.
So this dependency is clear, right? This dependency you have to understand that if alarm is functioning correctly, only when the gauge temperature is high, the alarm will go. The alarm will ring. Otherwise, it will not ring. Okay. So here you are given that the gauge is normal. That means it is in the standard operating conditions, right? And if FA is true, if FA is true and FA is false, that is not a problem. But if you are given that G is normal, will will the alarm ever go true? What can you say about this thing? Given that G is normal, will the alarm ever go true? That means will
No,
the
sir.
alarm ever ring?
No, sir, it
No,
won't ring.
that is correct. So yeah, that's why it is zero in both the places, right? Similarly, when the gauge is normal, right, and the alarm is working correctly, the alarm will not ring. So that's why it is a one here. And when gauge is normal, and the gauge is normal anyways, so even if it is faulty or not faulty, it will never go up because the alarm is false. Like the gauge is normal, right? So given that the gauge is normal, alarm will never go up. So it is false in both the cases, and
Sir,
alarm true is false in both the cases.
for the first one, when the gauge is normal but faulty alarm is true. So it and alarm is true. So it can ring, no, sir, because alarm is faulty.
So what does faulty alarm says? FA is that alarm is faulty, right?
So it will ring when it has not to ring, even when the gauge is normal. It is confusing a bit.
So alarm works correctly unless it is faulty. So if the alarm is not faulty, then the alarm works correctly, meaning that it sounds only if the gauge reading is high. You understand this statement, right? Did you understand this statement?
Means it rings only when the gauge goes beyond the threshold.
See, if the gauge is normal, even if the alarm is faulty or not, see, it will not ring because the gauge is normal. Alarm will trigger only when gauge is high. FA just tells you whether the alarm is faulty or not, but when will the alarm go up? The alarm will go up only when the gauge is high. That is what you have to understand. These values, that A equals to true, A is false, these will depend on whether the gauge is normal or not. If the gauge is normal, it will never go up. But if the gauge is high, that means the alarm should ring, right? But if the alarm is faulty, then it will not ring. And if the alarm is not faulty, it will ring. And if you take the negation case of this, that means gauge is high and false alarm, gauge is high and the alarm is faulty, it will not ring. And if it is not faulty, and if it is high, then it will ring. So A equals to false, or this bracket is 0. Is it clear?
Yes, sir.
Okay. Then there is this example of Bayesian rule. So suppose the alarm and gauge are working and the alarm sounds. Now calculate an expression for the probability that the temperature of the core is too high in terms of various conditional probabilities in the network. Okay. So what is given to you? It is given to you that the alarm and gauge are working and the alarm sounds. Okay. That means FA is false and FG is false, right? And alarm sounds means A is true, and you have to express the temperature. You have to calculate an expression for probability that the temperature of core is too high. Okay, and that is why the alarm went on, right? So you can write it as P of T given A, comma negation FA, comma negation FG, right? Is this clear how we got this expression? P of T given A, comma not FA, comma not FG.
Can you sir, repeat it again, sir?
Yeah. So what does the question says? Question says that the alarm and gauge are working. That means they are not faulty. So for FA we will have not FA, and for FG we will have not FG, right? And we know that the alarm has went off, and the alarm has there is an alarm, right? So and the alarm sound. So we have A. These are the values that we know, and we want to calculate an expression for probability that the temperature of the core is too high. So we have to generate P of T, and the T is conditioned on A, comma not FA, comma not FG. That is from this is where we will start from, right? So this value we would have to evaluate for the values of G. We have a variable for A, we have a variable of not FA, and we have a variable for not FG, right? But we don't know G, that is a hidden variable, right? So this is similar to what we did in John call Mary call example. If you remember here, this example for John call Mary call. Yeah. So you were asked to tell whether the burglary happened, given that John called and Mary called is true, right? So essentially, you expanded this entire thing to include all the variables in the network. right? So what are the variables of the networks? First, let us understand. So in the network, we have 1, 2, 3, 4, 5 variables. Okay. Out of that, we know A, FA, and FG. We only don't know what is the value of G, right? So we will include G, right? We'll include G. We'll include G as P of T conditioned on A, comma not FA, G, comma not FG. Okay. But what will be the value of G, right? What will be a valid value of G in the current scenario? Now, since we are using the assumptions from the above parts that we just did, right? Since the alarm sounds and the alarm is not faulty, since the alarm sounds and the alarm is not faulty, we can infer by watching this table, we can infer by watching this table that since the alarm sounds and the alarm is not faulty, that means gauge is high. Is this deduction clear? That alarm is not faulty and the alarm sounds, that means the gauge is high. Is this conclusion clear? If that is clear, then we can simply rewrite this expression as P of T, comma A, comma not FA, comma G, comma not FG. And the other term would be 0 because essentially that cannot happen. And then we use Bayesian rule to simplify this. So we get from P of T conditioned on A, comma not FA, G, comma not FG. We will write it as P of T, comma A, comma not FA, comma. So this is the simple Bayesian rule expression. And then we club together the conditional independence things, right? So A is dependent on not FA and G. Not FA is an independent variable. G is dependent on not FG and T. Not FG is dependent on T, and T is and temperature is a independent thing. So that is how we segregate the upper distribution. And for distribution on for joint distribution on the bottom, we write it as P of A conditioned on. So see, we have A not FA, G not FG. A is dependent on not FA and G. Not FA is an independent variable, and then G is dependent on not FG. So we can just simply write it as G not FG and P of FG. Then we eliminate the common terms, and we are finally left with P of T conditioned on A, comma not FA, comma G, comma not FG. It can be written as P of G, comma not FG, comma T, and P of not FG, comma T, and P of T, and P of G, comma not FG, and P of not FG. Right? Now, since we have in table the relation of G based on T and FG, we will try to use it. So we know that what is the value of P of not FG, that is already known to us from the table above, right? And we can just rewrite this expression P of G, comma not FG as P of not FG, comma T plus P of not FG, comma not T. If you don't get any calculation at any point, you can just let me know. Are you able to follow the calculations that we are making here or not?
Yes, sir.
Okay.
No, sir, if you could please repeat this breakups and all, then it will be good because chain rule is one thing that's known, but multiple factors, you have written it in one step. So that's becoming difficult.
So see, this entire joint distribution that you can infer from the network, right? So
That is
in
correct.
network,
That I understand. The base rule, this T given A not FAG not FG, that's given by this thing. That's correct. Then from next step onwards, if you can
okay.
elaborate.
So see, this P T, comma A, comma not F A, comma not G, comma not F G, this thing can be expanded using the network structure, right? we know that A is conditionally dependent on F only on F, A, and G. And once we know G, we don't need to map it to F, G, and T. Similarly, G is dependent on F, G, and T. F, G is dependent on T, and T is independent, and F, A is independent thing. Right? So we write alarm as dependent on not F, A, comma G. Right? Then not F, A is separated. Right? Then we write this G, that is the gauge reading, that is dependent on the temperature and whether it is faulty or not. Then we write gauge temperature, that the faultiness of gauge that also depends on temperature. So not Fg conditioned on T, and P of T. That is how we segregate this entire thing. Is this segregation clear or it is not clear? See, A is conditionally dependent on what? A is conditionally dependent on not Fa and G. So that's why in this term here we only write A conditionally dependent on not Fa and G, and it is, and since we know all the parents of A, it is independent of all its non-descendants. So we don't consider T, we don't consider G, and we don't consider not Fg. Right? Not Fa is a separate variable. It is not dependent on anyone. So we can just write not Fa. Now G is conditionally dependent on not Fg and T. Right? That part we are taking care of. And this Fg and T, this Fg is dependent on T. So we are writing not Fgt and P of T. So that is how we have broken down this particular expression on the top by using the structure of the Bayesian network. Okay. Is it clear now?
Yes, yes.
Hmm. Then we eliminate the common terms, and then it all boils down to P of G, comma not Fg, and P of not Fg. Okay. Now back to the problem, we can use the product version of Bayesian rule for the denominator. So P of, so it should be P of G conditioned on not Fg, and then P of G conditioned on not Fg will be written as P of G, comma not Fg, and then not of Fg, and we can just write it as P of G, comma not Fg. Then, since we have in table the relation of G based on T and Fg both, right? So we have to write it as G, comma not Fg, comma T plus P of G, comma not Fg, comma not T. We are essentially completing the joint distribution to get the final value. Okay. So how we are getting this? We are getting this from this table, that G, Fg, and T. So to get a value of G at any given point, we need both the values Fg and T. So that's why we're introducing T variable here. And when we add the positive, we also need to add the negative. So it is Pg, comma not Fg, comma T plus Pg, comma not Fg, comma not T. And then we apply the Bayesian rule here. So G, comma not Fg, comma T, P of Fg, comma T, Pt, and so on. Right? Now we know that P of G condition on not Fg, comma T is X. Right? Because gauge is not faulty and temperature is high. So gauge will give you the correct reading, which is high. So that is X. That is what we calculated above. That it is not Fg and T is high. So G will also be high and it will be X. Right? So this value is X. Similarly, everywhere this value will become X in all the places wherever this expression is, and 1 minus X if it is not the correct relation. So for example here, the temperature T, it is not high and the gauge is not faulty, but we know that the gauge's reading is high. That is happening with probability 1 minus x. So we write it like this. Now we just write P of T as M, P of Fg given T as N, and P of Fg given T as Q, and finally we land with this expression. So P of T we are taking M, Fg given T is taken as N, so not Fg given T will be 1 minus N, right? And Fg given not T we are taking as Q, so not Fg given T will be 1 minus Q. So this is 1 minus q, and p of not t will become 1 minus m. So the this is what it will finally be. So probability that the temperature is high, given that the alarm sounds and the alarm is not faulty and gauge is not faulty, will finally be boiled down to these values. And if you know x, n, and m, you can get the final answer. And this is how you will have to solve the questions that you have in the assignments. If you are able to distinguish, or if you are able to generate once you get the hang of how to segregate the values based on the structure of the Bayesian network, you will definitely be able to solve the question. So is this question clear? Are there any doubts on how we arrived at this final expression, or it is fine?
Sir, are these examples in the presentation folder? Sir, are these examples in the presentation folder?
No, they are not, but I can upload if you guys want. Like, I have no issues.
So these examples are like what, previous year asked questions, or like?
No, no, these are not from the previous years. These are some previous year did not even have an exercise this week.
No, sir, please upload this one because this will help us solving a lot.
Yes.
You can upload this. You will find this on Google. Like,
Sir, it's not actually Google getting some, but not these questions. We're
okay,
getting
I'll upload
some.
this. Okay, I'll upload this on Google. But I hope you were able to follow this entire example, like how the probability tables are constructed and how the values are filled and how the final expression is generated. I hope there is no question on that part. There is no confusion on that part.
Yes, sir.
Okay. So if there are no doubts, then I think we can end this session, and I'll see you guys on Friday. Thank you.
Sir, hello.
Uh-huh.
Sir,
Yes, yes.
I have one doubt in assignment 8, question number 6. If you have
In assignment 8, question number
assignment
6.
8,
Okay.
question number
Just, just,
6.
just give me a minute.
Sure, sir.
Week 8. Uh, assignment 8. And then we have question number 6.
6.
Yes, what is the problem?
Actually, I'm unable to elaborate after reading the videos lecture also. I'm unable to elaborate. I understood the concept of Bayesian network, but I am unable to elaborate the formula. I'm unable to solve this, sir. Would you please
So
help on
see,
this?
just like we did here, right? Just like we did in this example, you have to ensure that there are all the variables in the expression from which you want to generate the answer. So here it is asking that you have to find a probability of C conditioned on DNE, right?
Yes.
And it is given that P of A is this, P of B is this, P of C conditioned on A comma B is this, and so on and so forth. So just try solving this expression. So if you try expanding this, then what you will get and how it will look like, just try solving that part. Then you might get an answer.
Okay, sir.
And you might also need to change the order in which the terms are added or removed. Like that, you have to take care of very carefully, because Here it
So
is
if
asking
we
you C
start
condition.
taking all the variables into account, like P of A, B, A, comma B, comma C, comma D, comma E, then we expand. Then can we arrive at this C given D and D?
See, these kind of things were also covered in the lecture, right? Like this example, P of B conditioned on J equals to true, M equals to true, right? So for that, how did we proceed? So for B J comma M, we reduced it as P B comma J comma M and P J comma M,
Yes.
right? Then we wrote this J comma M, let it be alpha, but here you can also compute the value of J comma M. It is if it is given to you, or you can just try finding it that way.
Sir, by just like applying Bayesian rule and just like elaborating, we'll get the answer
Yeah,
for this.
but you have to remember one thing, that it is C conditioned on D comma E. So you have to correctly apply the Bayesian rule, that once you expand, then you might add more terms and remove terms from it. So for example, here, like you are adding E comma A, so you are adding all the values, right? All the values of E comma A. You're taking the sum over all the values. So like E true, E true, A true, E true, A false, E not true, A not true, and E true, A true, like all the four possible combinations. And then you break this entire thing P, B, E, J, M, and then you take the sum after pushing in, after like checking all the states. So here, like here, you can just do that PC condition on D comma I. You can solve it by PCDE divided by PDE, and from there you can just add all the missing variables that you have, and then you can get some answer. Then you'll definitely get some answer.
Okay, sir.
So, but you need to start with all the variables, because here also the values that are given, they have A, B, C, everything.
See,
And then
like
variable
actually you
elimination.
will add all the variables. You need not to start. Like here also we did not start, but then we added all the variables, right?
Yes, yes. I
Like you have
mean,
to start with
then
whatever is given in the expression, and then depending on whatever is missing or whatever is available, you do the calculation. Whatever is hidden and whatever is known. So here, for example, the evidence variables are DNA because they are known to you.
yes, given D and D.
Something like that. I hope I am not revealing any answers by any chance. Okay. So see, like just now, we did an exercise for the variables, for the temperature gauge variables. Here also you have a probability table, and once you get the final expression, you will get the answer. Anyways, I hope you won't have any hard time, because if you are able to solve this conditional probability thing, then it is fine. Then you will not face any problem. And just remember these three rules of d-separation, which I will reiterate once more, so that you don't have any confusion. So the first one is this, that if you have A, B, C such that there is a linear connection, then A is conditionally independent of C given B, right? The second rule is that B is the parent of A and C, then again A is conditionally dependent on C given the information of B. And then you have ACBDE, where D's are the descendants of B and D is the descendant of A and C. So information flow can happen between A and C if we do not.
Call me.
So A is conditionally independent, or information can flow between A and C if and only if we do have evidence that B or any of its descendants. So these are the three primary conditions that you need to know, that you must always remember when judging the conditional probability. conditional independence. Okay. Are there any more questions on this week's assignment that I should clarify or anything?
No, sir, it's all with you.
Okay. So if there are no further questions, then I would just end this session. And thanks for attending. Bye.
Okay,
Thank
thank
you
you.
so much, sir.
Thank you.
Thank you,
Thank you
sir.
so much.